In positron emission tomography, or PET, the objective is to obtain images of the brain's activity rather than details of its structure. To do this, short-lived radioactive chemicals are injected into the bloodstream of a subject or patient, and a ring of detectors maps the destination of these chemicals in the brain by sensing the emission of radiation in the form of gamma rays. Many of the radioactive isotopes used in PET are produced using a cyclotron. An accelerated stream of protons is directed at a stable target material, changing its atomic structure. To produce fluorine-18, a common positron emitter, the target material is O18 enriched water. During the bombardment, the oxygen-18 gains a proton and loses a neutron to become fluorine-18. The radioisotope is now incorporated into biologically relevant molecules. By far the most common tracer used in brain imaging studies is fluorodeoxyglucose, FDG, an analog of glucose. In FDG, fluorine-18 is substituted for a hydroxyl group. FDG is used in studies of brain metabolism to determine which areas of the brain are most active during a particular behavioral task. Because fluorine-18 can be substituted for hydrogen or hydroxyl groups in chemical compounds, it can be attached to a wide variety of molecules. For example, F18-fluoro-L-dopa is often used to study dopamine synthesis in the brain. Other commonly used positron emitters include oxygen-15, carbon-11, and nitrogen-13. The name PET derives from the fact that these radioisotopes are unstable and decay by positron emission. When the nucleus of the atom ejects a positron, abbreviated beta plus, the effect is to convert a proton into a neutron, an event that stabilizes the radioisotope. Positrons are basically positively charged electrons or anti-electrons. The emitted positron travels only a short distance before encountering a nearby electron. The two particles combine and annihilate each other, resulting in the emission of two high-energy 511 kV gamma rays in opposite directions. The gamma rays easily pass through the body and are detected by the electronics of the tomograph. Modern tomographs contain thousands of detectors arranged in rings surrounding the field of view. The tomograph software identifies gamma rays that are coincident, that is, those that are likely to have originated from the same annihilation event. By reconstructing the site of the positron-electron collisions, the concentration of the radioisotopes can be determined. In the reconstructed FDG PET image, areas of high activity and hence higher glucose utilization appear dark, while areas of lower activity are lighter. Researchers can also apply artificial color tables to the PET scan, facilitating the identification of regions of high activity. Note that these color tables can be either linear, for example from light to dark, or nonlinear, where hotter colors are used to indicate increased activity. PET provides a useful tool for isolating specific brain activity. By acquiring scans under both experimental and control conditions, the difference in brain activity in the scans can be computed and represented as a color-coded difference image that shows the regions of the brain that were more active during the experimental condition. Because PET measures activity rather than anatomical structure, PET scans are often superimposed on MRI scans from the same subject to make it easier to determine which structures are active. In behavioral studies, scans from the experimental group can be averaged and the activity of control group subtracted to reveal which brain regions are selectively activated.